Hello, everybody. And they have already given a very detailed introduction from me. So I'm a project lead at Ford, and I deal mostly with development in software models for control systems in autonomous vehicles. So today I'm going to talk to you more on battery technology and its energy management. And I hope that I meet your expectations and I'm able to render something useful from this seminar so that it'll be worth both of our times. Shall I proceed, Chinadurai?
Yes, ma'am. You can continue,
Okay.
ma'am.
It's not even 2. Do you want me to wait for a few minutes more? Or?
No, ma'am. We can start, ma'am. They will, participants will join.
Okay. Okay, then. To begin with, I thought I'll just have a small, detailed, okay, this slide, the heading, just ignore the heading. Just an agenda of what we are going to talk today. So mostly we will talk on introduction, the need of batteries, what are the types, what are the characteristics, and how to select batteries for any given purpose and how we can manage the energy in this battery. So before I delve deep into all that dry technical stuff, I thought I will give you something exciting, something fun to start with. So I thought I'll just show you what I work on, so that it'll become a little more interesting going forward. So this is a picture where we show off what are the electric vehicles that Ford is building. So one is the upper one is, as you can see in the picture, it is a Mustang, which is the trademark of the topmost elite vehicles in the Ford fleet. And Ford has recently unveiled the all electric Mustang. And the picture here is the most sold vehicle in the Ford fleet, which is the Ford F series F150, and it is built tough. It handles almost, it's the most sold vehicle in the US because it can function for all purpose. Like you can go on a picnic with it, you can do your heavy load jobs, you can do your daily activities with it, and so it's the most. So both the vehicles which are the most iconic of the name of Ford are now available in electric form, and they have both been unveiled, and you can see a lot of features about them on the YouTube, and you can also check them, and they are all available for sales from 2021 to 2022. So this is what is Ford moving towards, all electric vehicles on its most significant vehicles. And the area that I am most interested upon is, this is my research interest. So this is not particularly what we do at Ford, but this is most on my research interest. Since I finished my PhD in battery technology, I have tried to, keep up the legacy by having more interest in how batteries are going to evolve in the coming years in the in autonomous vehicles life. So I'll just show you 2 quick videos. After that, it's going to be all technical talk. So this can just be like a start off. So this is something which is called wireless charging of electric vehicles, which is a very important thing which can come up in the recent future, where you don't have to hassle with the cords, and you don't have, because the most negative impact that EVs have now is the charging. How do you charge it? You don't have as many as many charging stations as you have your petrol stations on the road. So that's the main hindrance that the customers are feeling to buy electric vehicles. What will you do if you get finished with the charge when you are on the road? There are no good charging stations. So for that, this will go a long way in solving those issues. So I'll just play this video. You can see that this is the charger. This is a wireless charging. It is based on the concept of nothing but Faraday's law, process of induction. So one coil is on this side, other coil will be at the base of the car. So as soon as both the coils come together, the induction, it will act as an inductor, and a power transformer basically, and it will start charging, and it will start, you have a electrical transfer between the 2 coils. You can see this video. So So it's all based on machine learning and artificial intelligence. The car has to, so this can be implemented in almost all parking lots. It can be implemented on the road so that you, as long as the car is parked, it can get charged like that. So it removes the hassles because of the cords. You can't have cords that again put it in and remove out, because it becomes very hazardous if you have rainy conditions or extreme snow conditions. The contacts will get spoiled if you are using it in rain in cases of cords. So these things are very helpful. And going forward, if this technology comes big, this is how they imagine the world to be in the future. See, your cars can auto park themselves, get charged overnight, so that they can repark themselves. If they are fully charged, they can move away and allow the next vehicle. All this is automatic. Then you can use the same energy to power your house. This is all smart connected house. So this is a video from Nissan. See, everything is connected. The car, the houses, the office network, the grid, everything is connected in a smart city network. So this is what is the envisioned future that's coming up in the battery technologies. Okay. So with this, I will move more into the topic that of today. I hope this was interesting. So the base of this everything is the battery storage. How good is your battery? How much can you manage your battery? How much can you play with the size, with the capacity and the power? Okay, the main thing, three things that will be of the interest of research in not only EVs but in many other fields. So just a brief history of batteries. So earlier we used to have only, I'm saying when history, I'm not saying very old, I'm just saying about early 80s as the start of the history, because batteries have evolved extremely fast. They have changed in the last 10 years. There have been an explosion in the battery energy technology, production, research, everything. So the early 80s is the most oldest form of batteries that we were using for the nearly 30 years. So we had just the 4A batteries, which were lead batteries, and then we had lead acid cells. Then we moved to nickel cadmium, metal hydrides, and now in the 2000s, we saw the advent of the lithium ion batteries. So this only changed the world, the lithium ion batteries. They have exploded the area of applications. They have exploded the capacity with which we work today. So the lithium batteries were the turning point in the history of the batteries. On the right-hand slide, the picture is maybe a little confusing, but what I wanted to tell you is, I'm just showing you the length versus time and the way the batteries are evolving. Not there is research going on the electron level, at the atom level, at a cluster level, at a particle level, at electrodes. What kind of different electrodes? There is no metal on earth which man has not tested yet for an electrode in a battery. And how finally the battery cells and the battery packs, how you manage. So research is going on at every stage of the battery development. It's not only at, so you can see what are the different research topics that are available uh, along the whole life cycle of that battery. So I think somebody has unmuted. Okay, so going forward, this I wanted to show you just what are the applications of batteries. Why do we need them? What is the most important thing? Why do we need battery? Because we need battery because it's an energy source. So energy source is the crux of any gadget, crux of any system, of the whole transportation system, electrical system, like that. It's the main crux. It's a source of energy, and it finds application in a variety of areas. Okay, so earlier we had smartphones, laptops, tablets as the gadgets that we regularly use in day-to-day life, and that is almost a saturated market. Okay, because we have reduced computers to shortest in form of even a smartwatch is a small computer on your hand. Okay, so that is a saturated market. Whereas when you see renewable energy, the grid, the stationary energy storage, which will come into play more in the future electricity grids, it's a growing market. Similarly, transportation is also a growing market. And this is the field of electrical engineering that we have. And I have also looked into some points of biomedical engineering, and I learned a lot of new things while doing this. So we use batteries. We do know, we almost use all of these equipments, like we have BP meters at home, we have sugar testing. So there are a lot of gadgets that we use in our day-to-day applications which use batteries. They're also used in your pacemakers. In pacemakers, it's mostly lithium ion battery, which is used with, which has a very long lifetime. So, but the batteries that are used in the cochlear implants, they are of rechargeable type. So they have, like, at one charge, they can hold up to 90 hours and they can have up to 500 cycles. So these are, and some batteries are there for, drug delivery by inside the body itself at the correct time, smart pills. So a lot of things are coming up in the biomedical sector also, where a lot of devices are based on battery technology. With this, I want to talk more on what is a battery. How do you understand how it functions? Okay, so first is electrical energy is converted into chemical energy to and fro while charging and discharging. So basically, it has an electrodes, it has an electrolyte. I won't go much deep into the explanation of how the chemical equations happen, but overall the concept is a battery will have cathode, anode, and electrolyte, which save the electrical energy in a chemical form. And when it is discharged, this chemical energy is converted into electrical energy and taken out. So you can compare the battery to a glass of water, like how much water is filled, that much is the battery is filled. That much you can say is the voltage that the battery can hold. And how much water you are taking outside, that is the current that is flowing outside. Okay, much similar analogy. But when we see the characteristics of a battery, it's not exactly a linear glass. It's more like this wine glass. That is, as the level uh, is, as the you start pouring water, at when the glass is narrower at the beginning, it will fill up faster. Whereas when you go up, it will fill much slowly. So this is how the voltage curve is. That is, at the beginning, it will charge at a faster rate. The voltage will increase, and then it will hold steady for the most of the period of time. And as it reaches the end, it will charge a little more faster. So this is your open circuit. We called it as an open circuit voltage curve. Okay, and this was measured at a constant current. So with difference in current, this line will shift. So this you can see is a tested value. So we can, I hope you can relate to what I'm saying. So this open circuit voltage is a very important factor while you are operating the battery. Okay. Here I'm having some definitions of the different, these are just names which you have to remember what they mean when you talk about a battery. Tomorrow, when I'm going to tell you different types of batteries, how do you differentiate? What is lead acid? What is a lithium ion? Why do we want lithium ion and why you want? So that time I will be using these terms. With these terms only you can compare the batteries. So one is the battery capacity, the first one. Battery capacity, it's the capacity of the battery. How much charge is there inside? It's given by this quantum mechanics equation. And then comes the state of charge. State of charge is the most important factor when you are going for battery management, as well as it's nothing but it just tells you in percentage form. Mostly we give it as a percentage. So it just tells you how much percentage of the battery charge is available. Whatever you see on your, generally when you say the battery SOC is 100% state of charge is there, means the battery is complete, full. Okay, like that. State of health. This is mostly concerned with how good the health of the battery is. Say, for example, newly ideal battery, new battery will have 100% state of health. But as you go on using the battery, the state of health of the battery will go on reducing. Okay, as the battery ages, the state of health goes on reducing, and we need to monitor the state of health to know the value of the battery. Then comes depth of discharge. Depth of discharge is like opposite of SOC. SOC gives you like 60% means there is 60% charge in the battery. Depth is 40% has been removed. Say again like a glass of water, half filled, half empty, like that. The filled is the SOC, empty part is the DOD. So depth of discharge, why we want to know is some batteries you can drain complete to 0% and then recharge them again. Whereas some batteries, if you drain to 0%, they will never charge again. So that also is a very important factor in choosing the application. Okay. Same way, for example, the SOCC, 0% SOC is 0% depth of discharge means it is 100% SOC full, like that. And capacity can be expressed either as AH or as a percentage also. AH is ampere hours. So what do we have for example, when you just say battery energy storages, we have two different types. One is primary and one is secondary. When you say primary batteries, they are non-rechargeable batteries. They are one-time use batteries. You use them, you drain them, and you throw them away. Okay, there is no recharging of primary batteries. Whereas the secondary batteries are all rechargeable batteries, which can be used again by there is what is the difference? How is it possible? The chemical reactions occurring inside the primary batteries are non-reversible, only one way. That electrolyte is converted and it is deposited on the electrodes, it dries out, that's all. Whereas in secondary batteries, the chemical reaction occurring inside the battery is reversible, so that we can reverse the reaction and we can reuse the battery. With this, let us go into the different types of batteries. So I will just show you a brief hint so that we can discuss more on other important parts. So lead acid batteries were the oldest batteries that were used. They started manufacturing in 1859, and they mostly had lead oxide and sponge lead as the electrodes, and the electrolyte used to be the sulfuric acid. And the specific energy, what do you mean by specific energy? Energy, whatever gives the energy, how many watts of power in 1 hour of time per kg. So depending on the weight of the cell also, the specific energy will then be the value that you get. And the efficiency used to be very high. 75% to 90% was a good efficiency factor. And with this, they had the advantages was it was the most mature technology. It was used for a very long period, but it was environmentally unhealthy because whenever you finish your lead acid batteries, you just throw them in the dustbin and they become a hazardous material for the environment. So with this came the nickel-based batteries. The nickel-based batteries had a lower efficiency and almost very less increase in the specific energy. But the advantage was they were having a longer shell life and they had a much drier construction. So the sulfuric acid now was replaced with separators, and and now it was able to implement the electrolyte in form of a gel. Okay? So that was an advancement. But it also was hazardous and it suffered from memory effect. Memory effect is something in the batteries, like for example, if you're using a battery, it goes to 40% and then you don't use it. After some time you want to reuse it, it starts from 40%, means it has very good memory effect. But on the shell also, if it keeps on losing charge and when you use it again, it now starts at 30%, means it has a very poor memory effect. So nickel-based batteries had a very poor memory effect. That is, even when you are not using there used to be a small discharge going on within the battery. Then we had sodium-based batteries. The sodium was kept in a molten form and it was surrounded by an alumina tube as a separator, whereas the sulfur acted as the electrolyte. Okay. Now, the difference here is efficiency was good, but the most important was they could be installed in a underground chamber, and you could build big batteries with this. Okay, so that was the major advantage of having the sodium based batteries, and they are mostly preferred in large wind farms for renewable generations. Lithium ion batteries. Lithium ion batteries started very late 1960s, and then they saw giant production from 1990s only. But you can see that lithium metal oxides and lithium salts were used as organic fuel. But you can see here the efficiency went up. Compared to the older batteries, they give very high efficiency, and the specific energy almost doubled now. They can give double the amount of electricity with the same weight. So that was what was the advancement, extreme explosion of opportunities for utilizing the lithium ion batteries. They had the highest specific energy per weight. They had no self discharge. They were having very low maintenance. And also we can have any different forms of a combination of lithium ion, because it's ion, so you can replace it with any metal ion. So a lot of it opened a very plethora of options to couple the lithium with. This is something called as the flow batteries. These are also large scale batteries, but since this flow batteries is the one that I did my research on, I thought I'll just put it in one slide. So flow batteries are something like you have huge tanks of electrolytes, and then you circulate the electrolytes. So you don't have a stagnant electrolyte. You have two electrolytes, and you keep on pumping the electrolytes into and outside the system. So this is something this breaks the barrier of that specific weight in this, because what happens is you can store the electrolyte any form. You can go up till any capacity depending on the capacity that you can afford to have in case of your tanks. Bigger the tanks, bigger the battery. So this was a complete different phenomenon that came into being in the late 1980s. And though we are still waiting to see them come commercially, but as far as research is concerned, they have given very excellent results in their performance-wise. More recent, we had metal air batteries, which are like having air as one of the electrolyte to go and combine with the zinc or any other metals. You had aluminium, lithium, zinc, iron, any metal, and then you allow air to, pump in and have a reaction and generate the current. So these are also mostly in research, and very slowly they are coming into the market. And more recent are the bio batteries and silicon batteries. So bio battery is a battery which uses, in which either one of the electrolytes are going to be a biological material. They will be mostly enzymes. So that is, it's an idea like, for example, if you have an implanted device in your body, why do you need a battery to be provided from outside? The electrolyte, sometimes most of the electrolytes are acidic in form, which is harmful for the body. So if that electrolyte is replaced by an enzyme, or it is replaced by your own blood flow, then it almost incorporates the entire structure in a very biological form. We now avoid the hazard, and it is more involved. So that was the concept that made people to think about it, and that's how the bio batteries have come into existence. Here, the in biological waste only, and electrical energy as is required for that pacemaker in very small amounts can be generated. So they have even found in 2013 research that where we can use microorganisms also in the form of an enzyme as a good candidate for a bio battery. So we are seeing still research going on in these kinds of batteries, and Another is silicon batteries. So this is more recent. Day before yesterday, Tesla conducted the battery day, and it was a different experience to watch it. Instead of holding the shareholders meeting in closed offices to avoid COVID infection, he made them attend the meeting in like watching in a drive-in theater. Everybody was sitting in their own cars, and all the cars are parked in front of a stage which has a very huge screen which is visible to everybody, and at the same time whatever is happening is live transmitted to the screens inside the cars. It was excellent the way they explained about what they're going to do in their future technologies. Tesla is banking heavily on silicon-based batteries. So we will see more, see the specific capacity. It's now 300% of what was with the lead acid. So we are still yet to know more about it. But these are some of the most advancements that are happening in the battery technology. So again, I'm just having a glimpse at this. So comparably, you can see just this comparison is to see why lithium ion rules the market today. You can see the power density is the highest in lithium ion, and the energy density is also the highest. So when I'm saying power density, it is mostly what's and for energy density, and same. So once lithium ion, we have said that lithium ion is the best as of now present in the market. There are many varieties of lithium ion batteries that are available, and out of these, okay, and out of these, the lithium iodide and the lithium manganese oxide, these batteries are the most used in lithium ion batteries, and the reason is because they are the most safest also compared to lithium cobalt. The lithium iodide has been found to be most easily manufactured and easily available in okay. Now, excuse me. We have now seen the different types of batteries that are available. Now we come to know, we come to like think on how should I know which one to pick? That means you should know what you want. So once you know your application, you will know how much of power is needed, how much of energy is needed. Power is something like how the voltage into current only, whereas energy, how long you need that power for. Say for example, I need 10 amps, say for example, I need 2 amps at 6 volts for 3 hours. So that is energy. So if you know your requirements, you will be able to easily pick on your battery, which is most, you know, suitable for your application. So once you know your battery types, then you know your application. Using that knowledge, you pick up the best battery which is suited to your application. In this, I have tried to show some, biomedical applications. So higher, very less power is required for pacemakers, defibrillators, and all those things. In that cases, we can go for very small batteries, okay, lithium ion batteries. Whereas if you go much higher, like cochlear implants, you can have a little larger battery since it's going to be outside and it is going to be recharged regularly. So mostly zinc batteries are zinc, I said, right, metal layer batteries, like that zinc batteries are most preferred for this. So that is how you do your ESS selection. And once the batteries are selected, then you go about forming the battery bank. Okay. So depending on your application, here I have shown a general electrical application type battery arrangement. So either you can connect the cells in series or you can connect them in parallel, and you can form grids also. What happens when you connect them in series? When you connect them in series, same amount of current is going to flow through them, but the voltage only will be added. So one cell, you get 3.6. Add 2 cells, you get twice that, 7.2. Add 3 cells, you get 3 times the voltage, 10.8. Like that, the voltage goes on increasing, whereas the current will remain the same. Since the current is same, the capacity will be the same. Okay. Whereas if you're connecting them in parallel, the voltage is going to remain the same, whereas capacity will double for each. So one battery, you have 3,400 milliamps. For two batteries, you get 6,800 amp hours, whereas the voltage will remain 3.6. So as you go on adding your batteries in form of a grid, you can go on finding what type of what voltage and what current ampere hours you can form. Depending on your requirement, you have to build your packs. So am I going too fast, Chinadurai? Or is it
No,
okay?
ma'am. It's
Okay.
normal only. You can continue, ma'am.
Okay. Thank you. Go ahead. So this is now we go more on battery management things. So first, before understanding what is battery management, you need to know what happens when you are connecting so many batteries in parallel and series. What can go wrong? Okay. So thing is, all cells, they may look identical. Say for example, I'm showing like this, but not that this cell is going to be exactly like this, exactly like all cells can never be treated equal. So what happens is when they are in series, say for example, one cell loses some strength, it loses faster, the electrolyte is little drained, or it may happen due to any fault in the manufacturing, or anything can be the reason. Thermal, environmental conditions, wear and tear. Because of anything, if one of the cells is having a defective output, say if instead of 3.6 volt, it's giving you 2.8 volts. So overall, what happens is the current will keep flowing. But once this battery starts damaged is this start performing low, obviously you can detect the performance of the output also will go low. So you can see a drop in the voltage. And when this battery is completely damaged, it becomes an open circuit. Okay, that is, it completely fails. Though all batteries are good, because of one single cell also, the entire system can become faulty. Whereas if you're connecting in parallel, if one battery is failing, it will be an open circuit, whereas the other batteries will keep functioning. Okay, so you can replace this battery. But once, say for example, all are performing good, this battery went away. So this is a better case. Others are still performing. Whereas if short circuit occurs, say for example, more salt was deposited on the electrode and there is a short circuit between the positive and the negative cathode, this will be less hazardous, whereas this short circuit will be more hazardous. So both kind of things have their own advantages and disadvantages. And also for all these things, we need to keep an eye on the functioning of each cell in a battery pack. See, you can see this first figure, though the SOC of the battery pack is going to say the average of 70%, it doesn't mean all three are going to be 70%. One will be 90, one will be 70, one will be 60. We need to avoid these kind of things. What happens is this one guy who takes the most of the load is going to be the one who's going to fail like this. So there should be equal loading among the batteries. Only then it will live for a very long time. So that is only called cell balancing. You need to balance the cell to function as a combined unit. So how will you do that? We have two methods. One is called active balancing. Another is called passive balancing. So active balancing is nothing but what passive balancing, I'll say first. Passive balancing is nothing but what you do is you take the lowest battery and you try to discharge whatever excess is there in other batteries through a maybe a backup circuit. Okay, it will take the lowest battery level. So in these three batteries, 60% is the lowest battery. So what it will do is it will fix the other 2 to 60% and drain the excess outside. That is only passive. So all are 60 equal. But in this case, we lose the energy. And when you say the energy is lost, that means it is removed in form of heat, which is bad for the battery life. That's why we go for active balancing. What active balancing does is it keeps, it involves a little more complex circuitry so that the current is discharged from the higher level of battery, it discharges the excess to others till they are all equal. So this is like sharing. The guy who has more, he will share to the guy who has less until they are all equal. So this involves more complex logic and a complex circuitry. Okay, so next when I talk about energy management system, I hope you will understand when I say cell matching or cell balancing. Okay, battery management. Battery management, mostly the whole system, it generally consists of the battery cells, charging circuits, and the battery management unit. What do you see mean by a battery management unit? It is the brain of the battery pack. It will tell the battery, do this, don't do this, charge now, discharge now, stop now, open circuit, everything it will take care of. Why? Because the main objective is to protect the battery. So it has to protect the battery. How it will protect the battery? By having a switch which will be operated based on the SOC. As we already saw, SOC, I told you, it's the state of charge. The state of charge is 0 to 100%. 0% is empty battery, 100% is full battery. We should always ensure that the battery remains in the operating period from 20% to 80% only. You should not drain below 20%. You should not overcharge above 85%. Like that, every battery has its own SOC limits, we say. What do we say for this? SOC limits. As I already told you, the depth of discharge opposite of SOC. So for example, if you are draining a battery complete 100% depth of discharge, it's very bad for the battery. Similarly, we are trying to limit that by fixing the SOC limits. Now the BMU should take action. It sees that charging started, maximum charge 85 to 90 has been reached. What it will tell is, it will ask the switches to disconnect the battery from charging further to prevent overcharging. Similarly, discharge is occurring. Your battery is draining below 20%, reaching 16, it will disconnect and switch off, saying that it is below SOC limits. So whenever you see in your mobile phone, it shows 10% battery. You still go on playing your game and suddenly it will switch off. You will say, oh my God, I still had 7%. Give me that 7%. It won't give you the 7%. That shows 7%. But actually, in your battery, there is at least 17% available with a 10% which is not shown to you. That is the battery management unit acting there. It protects the battery from overcharging or over discharging. Second is protection from overheating. So when does heat happen? Whenever there is some abnormality happened, something you broke it, mechanical abuse was there, electrical abuse, overcharging or over discharging, or thermal, you are heating that thing. So whenever such thing happens, the batteries will get overheated due to deformation or due to separator being collapsed, or the electrolyte will break, or the electrolyte will enter into somewhere into the insulations. So any of this can happen. But at that time, what happens is, it's not a small thing. What happens is, when the electrolyte is coming out, or when the electrolyte is having a bad reaction to thermal, then it releases more heat. The heat increases the more the damage again creates heat. So this cycle is very fast, and this is called a thermal runaway. So what happens is, the heat gives rise to more abnormality, the abnormality gives more heat, and within some time, even if it is a cell pack, from one cell, it spreads, the heat spreads to all other cells, and everything collapses together, and there will be a explosion. If it is more severe, it will be an explosion, or at least a fire will be there. So we have to avoid this at any cost. Okay, we have seen even huge EVs get blown up because the battery got overheated. So that's the most dangerous thing in a lithium ion battery. It's called a thermal runaway. Okay, so one single cell, if it blasts the entire battery pack. Okay, so how can we protect it from thermal runaway? That also the battery management unit only does. So how does it do it? It monitors the voltage of the battery with overall battery. It monitors the voltage of each cell, because one cell it damages, it spoils everybody else. Okay, so it's not only enough to see the voltage of the entire pack. You have to see the voltage of each cell. Only then you will be able to protect the entire thing. So you have to monitor the voltage of each cell. You have to maintain the state of SOC limits of the batteries that are there. And finally, you have to have a excellent and very fast acting charging and discharge MOSFET switches, which can help in, you know, reducing the, which can disconnect the battery and protect it in cases of any abnormalities. Plus, there should always be a constant monitor for state of health, Coulomb counting, and cell balancing. State of health, I already told you, it determines the health of the battery. How many useful years are still there? How much, say 100% means, say if a battery, a lithium ion battery, I'm saying it can run up to 7 years, the state of health is 100%. But as the battery becomes aged, that number of years is coming down. Similarly, the state of health also will come down. Coulomb counting is amount of charge in the bottom. Say, for example, in your laptop, the charge that shows at the bottom, 100%, that's based on the Coulomb count. Okay, so this is what the battery management has to take care in a battery. Apart from this is in case of protection, right? Apart from this, overall, there is a whole process of battery management that has to happen. Okay, see on this right side, I have shown you an image of the battery. It has active portion and a dead portion. So as the battery becomes old, the dead portion goes on increasing until the whole battery dies off. So this dead portion is an unusable part, and this reduces the amount of energy that is available at any point of time. Okay, and there is always an empty zone. Empty zone, I already told you, we are limiting the SOC limits so that some part is left off for protection. So the available energy is only this much. So we need to keep an eye to know how much of battery is used at any time. For that, how you do it? As soon as the new batteries are manufactured, they have an inspection. Then where they are used, that application area has to be prepared so that it is helpful for the operation of the battery. It should not, the heat, the amount of heat that the battery can tolerate, that should, that is a very important factor in field preparation. That is, the instrument should be well enough that it is lesser than the tolerable limits of the batteries. Then periodic capacity check. Exactly what I told here. You have to periodically check how much of state of health is left, how much of available energy is there in that battery. And once you see that the entire battery is gone, you need to have a retirement process. You need to have a proper scheduling where you remove the battery and you dispose it in a correct manner. Some batteries are reusable. You can give it back to the company, and the company will do something and recycle it on a larger basis. So that is called servicing of the expired batteries, and then replacing the batteries. So this is also a process of battery management that goes on in larger systems. With this, you have some battery test systems. We have to regularly test the battery. But just by looking at the test, you can't say it's good or wrong. It's just like your weather forecast. So not as bad as that, but still battery testers will provide only a few estimations. So you need to have a different approaches. You need to have different methods to finally assess that this battery is good enough. Because nowadays battery applications are becoming more and more critical. When you see some of the major ventilator systems which run on batteries, which they are very critical systems. You can't have even one faulty battery in that case, because one faulty battery will now be a one life lost. Vehicles, automatic vehicles, which are now on the road, you can't have one battery loss, because that will be 4 to 5 people loss of life. So you can't take risk in battery assessment things. You need to have a lot of different strategies. You can use a lot of tools, test systems to find the state of the battery that is. And some other common factors are, you can measure the internal resistance, capacity, Coulomb pounds, and you need to have a very good battery management to allow for scheduled retirement like that. So with this, I think I can come to the last slide, conclusion. So overall, we discussed what is the need for the energy storages, what are the characteristics of the batteries, and we discuss battery energy storage in depth, and how to select a battery. We learned the different types and what applications will need how batteries, and the recent trends also I tried to show you some. I hope so. And finally, I talked to you about the battery management. So I hope with this I conclude my session, and I'm really thankful to Chinnadurai and the management and the HOD of SKC College of Engineering, Coimbatore, for giving me this opportunity to present in front of you.